Let us now study properties of conductors at electrostatic equilibrium. So what's a conductor? A conductor is a metal or any substance which allows charges to flow through. So that's what is a conductor. Now let us take a wire here. Okay. Let this be a wire, and in that electrons flow. There are many electrons there. Okay. Let me write the electrons like this way. There are many electrons like this way, but if you notice that each electron will go in random directions. This will go this side, say example, this will go this side, this may go this side, this may go that side. So what happens is there is no net motion. All the electrons do not go in one direction only. Okay, they go in random directions. So we can say they are in electrostatic equilibrium. Let me write that. So here what happens is there is no net motion of electrons in a particular direction. So the whole wire is in the state of electrostatic equilibrium. So that means what? The electrons go in random directions and they cancel each other. Okay, that means the electric field cancel each other. So you can see they are in electrostatic equilibrium. That means the electrons don't go in particular direction. Now let us see some important properties of conductors at electrostatic equilibrium. Now let's go to the first property. The electric field is zero everywhere inside the conductor. This is true whether the conductor is solid or hollow. So if you take a conductor, inside that the electric field is zero. Okay. So whether we have a solid conductor or a hollow conductor. Solid means a full wire, okay, which is fully there, or a hollow means it's like a, say example, a hollow sphere or a pipe. Okay. So let's see an example. Now let me take a conductor here which is in shape of a square. Let's imagine this to be a conductor or a metal. Then electric field comes from left side to right. So these are the electric field lines: first, second, third, and the fourth one. Okay, so this is the electric field E. Now the electric field will go inside the conductor and will come out also. So 4 field lines go from left side, 4 field lines will come from right side. Now let us see what will happen inside this. Okay, so this electric field is due to the positive charges, so it will attract the negative charges. So you can see the negative charges will go to this side. Okay, inside that the negative charges, all the electrons, negative charge means the electrons will go to the left side, but the positive charges will be repelled. So you can see the positive charges will be here. That means the protons, they won't move easily, they go to opposite side. Now if you notice that, let us see what will be the electric field inside this wire or inside the conductor. Let's take a point here. Let me take a point here. Now if you notice that the electric field goes from left to right, inside also will go from left to right. This is the external electric field. This is the external electric field. But if you see inside, there is also an internal electric field. Okay. I'll choose another color here. Let me choose this color. So that's the internal electric field. Okay. This is the internal electric field. Okay, why it's internal? It starts from positive and goes to the negative. So this is the, so this side will give us the internal electric field E internal. Okay, that goes from positive to negative. If you notice that these two are in opposite directions and equal magnitude, so they will cancel each other. Okay, now if you notice that this happens, okay, the positive and negative charges moving from each other, it happens in very fast. Okay, the time it takes is around 10 power minus 16 seconds. I'll write that down. So the time is said it is around 10 power minus 16 seconds. Okay, that means it's almost instantaneous. Okay, so I reset the point here and drawn this way, but when you write an assignment, you must write the full things in the textbook. Okay, so this is the first point. The electric field is zero inside the conductor. You can take any kind of conductor, it may be solid or hollow, but the electric field will be zero. Okay, this is the first point. Now let's go to second one. Let's go to second point now. There is no net charge inside the conductors. The charges must reside only on the surface of the conductors. That means inside a conductor there is no charge. Okay, first we saw there is no electric field. Now they're saying second one is there is no charge also. So whatever charge you give on a conductor, it must be on the surface only. So let's see that. Let me draw a conductor here. It can be any shape. Okay, this is a conductor here. Then let me take Gaussian surface here. Okay, let's choose this color here and draw a Gaussian surface. It's inside the conductor. So this one is the Gaussian surface. Gaussian surface. Okay, now let us see what will happen. So whatever charge we give, it will be on the outside only. Okay, the charges that we give will be outside only. There is no charge inside. So electric field will be 0 inside. Okay, so inside a conductor we have saw that the electric field is 0. So let's use it now and use the Gauss law and find this thing. So in this case you see the electric field E is equal to 0 inside the conductor. Okay, inside the conductor the electric field is 0. Inside the conductor the electric field is 0. Now that we know, first one we take. Then use the formula for electric flux. Phi is equal to E into A. Okay, this is another form here. Then we have this phi is equal to Q by epsilon naught. This is from where? This is from Gauss law. From Gauss law. Now we can equate them. Okay, equate both the equations. Equating, we can take this is 1 and this is 2. 1 and 2. What happens now? Left hand side is equal means right hand side must be equal. So E into A is equal to Q by epsilon naught. But we saw E is equal to 0. So E was 0. So 0 into A is equal to Q by epsilon naught. A cannot become 0. Okay, epsilon naught cannot become 0. So it means the charge is 0 here. Okay, so what does it mean? From this thing means charge Q is equal to 0. So there is no net charge inside the connector. Q is equal to 0 here. Okay, so whatever charge we give, the charge will be on the surface only. There is no charge inside the connector. Okay, this is the second point here. So let's go to third point now. The electric field outside the conductor is perpendicular to the surface of the conductor and has a magnitude of sigma by epsilon naught, where sigma is the surface charge density at that point. So the electric field outside the conductor is perpendicular to the surface and it has a magnitude of sigma by epsilon naught. So first let's see line by line. The electric field outside the conductor is perpendicular to the surface of the conductor. So this one will take. Okay, let's see how the electric field is perpendicular outside the surface. Let's see that now. So for this I will draw a conductor like this way. Imagine this is the shape of conductor, and then we have an electric field there. Okay. So let me draw the electric field in this direction. Okay, E. Now the electric field will have two components now, parallel component and a perpendicular component. So this part will be the parallel component, that is E parallel, and this part will have the perpendicular component, that is E perpendicular. Now if you notice that E parallel, okay, if the electric field is parallel means if there is an electron here, what will happen? The electron will be pushed by the electric field. It may be pushed or attracted by the electric field, and there will be a movement of electrons on the surface. Okay, so electrons will be moving on the surface, but we see that electrons do not move on the surface, okay, from one point to another point so easily. So the electric field must be perpendicular to the surface, it's not parallel. Okay, and you can see if the electrons move on the surface means they'll have an acceleration, but there is no acceleration. So electric field is perpendicular. This is the correct one. Electric field is perpendicular, it is not parallel. Okay, so this electric field is perpendicular, is the correct one. I put tick mark here. So now let's see at a surface what happens. So we saw the electric field is perpendicular. Now I'll take this 4 lines as electric field. This is a parallel electric field. This is a parallel electric field like this way. So this is E vector. This is a parallel electric field. Now we have a surface which is curved. The surface is like this way. It is curved like this. Okay. This is the surface or conductor, you can say. This is a conductor on a metal. It's curved. So what will happen? How the electric fields will go? Okay, in this case, what will happen? Will they be parallel or perpendicular? Now the electric field will come here. It will hit the conductor like this way on this part. At here like this. At here it will curve and go hit this part. At here it will curve and touch this part. If you notice that at these points, okay, even though the conductor is curved, at these points the electric field is perpendicular. There is a right angle here. You can see everywhere there is a right angle. Okay. So, and we know electric field starts from positive, ends at the negative. So here inside this part must have the negative charges. Okay, or by induction it will become negative. Now what will be the electric field inside the conductor? The electric field inside the conductor will be 0. Okay, so we know that so electric field is always perpendicular to the surface of the conductor. Now let's go to next one. That is, we have to see or prove it as a magnitude of sigma by epsilon naught. Let's prove that now. So now let's go and see the continuation of the third point only. Okay. So let me choose a conductor like this way. This is a conductor here. Okay. On this conductor, let me take a small area and draw a Gaussian surface. So this will be giving us the Gaussian surface here. Okay, this cylinder is a Gaussian surface. It will also go inside the cylinder, inside the conductor also. Okay. Now the electric field will go outwards like this way from the surface. It's a positive charge. Imagine it's a positive charge, so electric field will go outwards, and the area of this Gaussian surface will be A, or the area of the surface is A. Okay. So what will be the flux here in this case? Flux phi is equal to EA. In this case, the electric flux will see that is phi is equal to EA, that we know. Then we also know from Gauss law that phi is equal to Q by epsilon naught. This is from Gauss law. Okay. So equating both the equations or comparing both the equations. Okay, this is one, or you can just write here 3 and 4 itself because you wrote 1 and 2 already. So this is 3 and 4. So equating equations 3 and 4, because left side is equal means right side also must be equal. So let's equate 3 and 4. So what we have on left side is EA is equal to, right side we have Q by epsilon, because left side is equal means right side also must be equal. We are equating right sides. Okay. Now let's see what's meant by Q here. Q means a surface charge or charge on the surface. Okay. Now we have something called surface charge density, that is sigma. Sigma means surface charge density is equal to Q by A, charge by area. Now what we do is just cross multiply this area upwards and rearrange. So we get Q is equal to sigma into A. Let's substitute this here. So what we have is EA is equal to sigma into A by epsilon naught. So A and A will cancel, and then we have the electric field E is equal to sigma by epsilon naught. Sigma by epsilon naught we get. Okay. Epsilon naught. So this gives us the electric field at a point on the surface. Okay. E is equal to sigma by epsilon naught. Now let's go to the fourth point there. So let's see the fourth point now. The electrostatic potential has the same value on the surface and inside of the conductor. That means on top of a conductor, if there is 10,000 volts, inside also there will be 10,000 volts. Okay. Let's see that now. And one more thing we know, that the conductor has no parallel electric component on the surface. That means we can move a charge anywhere in the surface without doing any work. Okay, so for that let me choose a surface here, or let's take a sphere. Okay, this is a metal sphere, and then we give positive charges to it. We can also give a negative. Okay, so this is the positive charges we are giving here. Now if you want to move this charge from one place to next place, okay, I moved from this side to this side. So what happens is we need not do any work. The work done is 0. Okay, so why? Because it's an equipotential surface. That means there is all the surfaces have the same potential. Okay, that means at this point the voltage may be say 10,000 volts. At this point also the voltage will be 10,000 volts. So because they're same potential, we don't, the work done is 0. So now we know two things. That's there is no parallel component, sir. Then the work done is equal to 0. Okay, between, to move the charges between any 2 points on the surface, work done is 0 to move charges between any 2 points on surface. And let's see second point also, second thing to remember. So now we have this surface here, or charge on an object. Okay, let me draw another shape. Okay, erase that and let me draw on like this way. You can draw any shape. Now the electric field is 0, the same inside the conductor, the electric field is 0. That means what, on the top surface whatever potential is there, see at top surface potential maybe say 15,000 volts. Okay, the same potential must be inside also. Okay, this is what we know from the fourth point. The electrostatic potential has the same value on the surface and inside of the conductor. So whatever potential we have, the same potential must be inside also. Here 10,000 means here also must be 10,000. That's why the electric field is 0. So these are some of the 4 important points for properties of the conductors at electrostatic equilibrium. This is an important 5-mark question.